Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of Organic Chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we're continuing our investigation of the derivatives of carboxylic acids. Specifically, we're looking at amides and the reactions thereof. Now, in the last Scribblecast lecture, we examined the reactions of hydrolysis of amides into carboxylic acids and carboxylate anion. What we want to do now is take a look at reduction reactions. In fact, we're going to look at the reduction of amides, and then we're going to contrast that to what we learned about reduction in esters. Now, if I do a reduction reaction of an amide, I need a powerful reducing agent. For example, if I have RC double bond O, and let's give ourselves some substituted amide, let's say an NHCH3. I can react this molecule with lithium aluminum hydride. Lithium aluminum hydride is a powerful reducing agent, and you need that power to reduce a carboxylic acid derivative. It's usually reacted in a solvent, so you often see ether written here. But even if ether is not written, you assume ether to be there. And then in step 2, because once we're reduced, we'll have an amine, we want to be under neutral conditions. Otherwise, if we use acid, we'll protonate the amine. So we usually just use H2O. If you carry out this reduction, you effectively cause the oxygen to be removed, and you get 2 hydrogens in its place, and you have a secondary amine if your nitrogen had 1 substituent on it in the amide. So there you go. If the R group was an ethyl, let's say in this case R equals CH2CH3, then my N-methyl propanamide remember the nomenclature is derived from the carboxylic acid. Drop the oic acid, propanoic acid, add amide, and methyl because there's a methyl off the nitrogen. The common name, of course, is N-methyl propionic acid becomes propiamide. Propionamide. Interesting. Propiamide. What this forms, of course, is, okay, if we check this, N-methyl propan-1-amine. Okay, so N-methyl. If I was naming amines, longest carbon chain is 3 carbons. The nitrogen's off carbon 1, so it's a propanamine, propan-1-amine. Running out of room. There we go. Okay, and N-methyl propylamine would be the common name. Okay. How does the reaction proceed? We should take a look at the reaction mechanism to examine how the oxygens are removed. Of course, the first step is close approach. So my R group, I'm going to keep that ethyl. Let's look at the exact same amide. I may use R. And we take lithium aluminum hydride. So the aluminum hydride minus reacts Remember, hydrogen's more electronegative, so we have a delta minus here. Delta plus on aluminum. And on the carbon, there's a delta plus and a delta minus. And effectively, the H minus is attracted to the carbonyl. This breaks the pi electrons. And the aluminum, which now gains an empty orbital, right? AlH3, because the whole molecule is minus, AlH3 is neutral, but it does have an empty orbital. You end up producing, I'm going to use R for ethyl, CHO AlH3. And we have the NHCH3. Right. Now at this stage, what happens next is determined by the leaving group ability of two possible leaving groups. Normally what we would see is the oxygen dumping in electrons, stabilizing a carbocation by resonance, and kicking out this leaving group. But the question we've got to ask is, who is the better leaving group? This or this? Certainly R minus will not leave, H minus won't. So once you get to this situation, you only have two choices. The weaker the base, the better the leaving group. It turns out that NHCH3 minus is a pretty powerful base, more powerful than the aluminum oxide. And hence, what leaves is the OAlH3. It's the better leaving group. And so what happens is you end up getting RCNHCH3 plus H, and that's resonance stabilized by the nitrogen with R, C, double bond, NHCH3, positive on nitrogen, H. And so what left was minus OAlH3 minus. Okay. And this material will go off and be left to react. Now, what happens is another aluminum hydride very quickly comes in and adds in the same manner H minus to the carbocation. And the aluminum may interact with the lone pair of the NH. So you'll end up with something like this. RCH, H, NH, CH3. You may, because of the empty orbital on aluminum, have an interaction with the AlH3. The final result in this whole reaction once you add in the H2O in the second step is you destroy the alumina salts and you've got RCH2 NH CH3. Now let's come back to this stage. Aluminum AlH3, remember right here, has an empty orbital. You might say, why does the aluminum AlH3 bind to the oxygen? Why not bind to the nitrogen? Make that a good leaving group and restore the carbonyl. Remember, oxygen bears the negative charge here. Effectively, oxygen with a negative charge can compete as an electron donor with nitrogen that has a lone pair. the rationalization that the OLH3 group actually leaves suggests that the aluminum is binding most strongly to the oxygen. Now what's interesting about this is if you compare this reaction, so let's draw this reaction out again, compare this reaction to what would happen in the analogous ester. Okay, so I've got R will be ethyl again. Okay, so I've got R, C double bond O, NH, CH3. I treat this with lithium aluminum hydride. Step 1, step 2, H2O. And I get rid of the C double bond O. R, CH2, NHCH3. Now compare what happens to the analogous ester as we covered it in the last 2 or so scribblecasts previously. So we'll have a methyl ester instead of the NHCH3, an OCH3. So 1 lithium aluminum hydride and 2 H2O. Well, if it proceeded the same way, the double bond O would become a CH2, and I would form this molecule. This would be proceeding the same way. In fact, let's draw that molecule in a different color. What would form if I did the same thing that an amide does? But if you recall, this type of reduction in esters does not produce this at all. What actually forms? What actually forms is R CH2OH plus HO CH3. Why the difference? Well, it has to do with the way aluminum hydride reacts and the intermediate it produces. Lithium aluminum hydride, H-, will react and put an H- on the carbon of the carbonyl. In other words, in the amide case, I get as intermediate this guy. And he binds to ALH3. In the case of the ester, I form the same intermediate. H- adds to the carbonyl. Pi electrons move out, making an O-. The O- interacts with ALH3. Now, here's the deal. What path or what product you will form will depend on what group leaves. We've already determined that in the case of the amide, this group is the better leaving group. NHCH3- is in a very powerful base, very poor leaving group. OALH3 can compete with that. and it leaves. When it leaves, the NHCH3 is still attached to the carbon, as shown here. However, in this case, OCH3- would be the leaving group. OCH3- is a much weaker base than NHCH3-. Because it's a weaker base, it's a better leaving group, better able to compete with the OLH3. In this case, the OCH3 leaves because it is a weaker base. If it leaves, then this will split when it leaves into R, C, O, 2 lone pairs, ALH3, H plus, and OCH3-. When you throw in the H2O will hydrolyze the aluminum, protonate the oxygen, and protonate the OCH3-. Note, before this happens, it gets attacked by one more AlH4-, which will add a CH2. So whether the molecule produces 2 molecules of alcohol or 1 molecule of amine is determined by leaving group ability. If the amide had reacted like this, what would you have gotten? I'll draw it in black. Well, we would have added H. We would have gotten R, CH2OH, plus NH2CH3. If it acted like ester and the N had been kicked out. But indeed, that doesn't happen. Okay, so there you have it. Esters react by a different pathway simply because they have a slightly better leaving group in the alkoxy group than an amide does in its NHCH3-. Well, as we're comparing to ester chemistry, one of the important things we covered in esters were polymers of esters, called polyesters. What we want to do now is talk about and examine some very important polymers referred to as polyamides. Polyamides. Polyamides are very important in the biochemistry of living cells. Amino acids connect together through amide linkages, forming polyamides. These are referred to as peptides, proteins, and enzymes. Synthetic polyamides are used in industry. An example of a synthetic one is nylon, six. This is synthesized from hexane dioic acid or adipic acid. So that's a dicarboxylic acid with 4 CH2s in between it. If I take this and react it with SOCl2, SOCl2 converts carboxylic acids to acid chlorides, making the carbonyl chloro unit much more reactive. See, we couldn't react the carboxylic acid with amine, it would just deprotonate it. But acid chlorides can react with amines to make amide bonds. So hexane dioic acid becomes hexane dioyl dichloride. Okay, maybe we should write that out. Well, let's use adipic, the common name. I'll just write one out. Adipic acid becomes adipyl, dipple. And there's two chlorides, and you say dichloride to indicate both carbonyls have been converted to isochlorides. Okay, so dipple dichloride, and we react this with what? Well, we're going to react it with hexane diamine, 1,6-hexane diamine. So we have NH2. We have 6 carbons. (1,6-hexane diamine) or hexamethylene diamine is the common name. That's a good one to write out. Hexamethylene. Remember, a methylene is a CH2. By saying hexamethylene, we're indicating there's 6 CH2s, and off of the ends of the CH2s is 2 amines, so diamine. Diamine. Okay, so hexamethylene diamine's a common name. 1,6-hexane diamine is the IUPAC name. Well, what do we get in this case? Well, we get a very long polymer. We have an NH. Okay, so I'll put a bracket here indicating it. It's attached to a CH2 that has 6 CH2s, of course. So here's CH2 4 times, CH2. It makes an amide linkage to a C double bond O, and that C double bond O is part of a 6-carbon adipic acid, actually a diacid. So CH2 4. And this will be the amide end. Okay. And N indicates that this whole unit keeps repeating. It's called Nylon 6,6 because each diamine and, if you like, dioic root has 6 carbons in it. So there's a 6-carbon chain, hence the term Nylon 6,6. Now we can actually make this readily, with this type of molecule, very related, very similar polymer, from the molecule hexanyl 6-lactam. Now if you think about it, a hexanyl 6-lactam, a lactam has an amide. It's like a cyclic ester. So we must have seven carbons. Oh, sorry, 6 carbons. Here's an NH. I'm going to put dots so once this gets reduced. So we've got so those are my carbons. I have 6 carbons, so this is a hexane. We have a double bond O off of here, so this is a cyclic amide, just like a cyclic ester. And we learned that cyclic amides are called lactams. This molecule is hexanyl because there's 6 carbons. 6. So 1, 2, 3, 4, 5, 6. The amine off carbon 6 cyclizes, and it's a lactam. I'll put the M down there. Hexanyl 6-lactam. Now if I use hexanyl 6-lactam, things change a little bit in the structure of the polymer we make. Okay? See how the polymer is consisting of N, 6 carbons N, then C double bond O, 4 carbons, C double bond O. Well, in this case, when this opens up, we're going to have N. At the end of the chain will be a C double bond O. So this becomes a C double bond O. And then on the next chain that attaches will be the N H. So we've changed it slightly. Okay. And it's not nylon 6,6, where you have 6 carbons from one diamine and 6 carbons from a dicarboxylic acid. But this is simply nylon 6 now. Nylon 6 just switches the NH and C double bond O here in these two positions. And it just repeats the NH with 6 carbons, C double bond O. Another NH with 6 carbons with C double bond O. Okay. Nylon 6,6 possesses alternating dicarbonyl diamine units. When it was like this, you had a diamine and then a dicarbonyl. Diamine, dicarbonyl, and so on. However, when you switch those two in the polymer, and of course we've got to have one more carbon here when we do that. Got to have 6 carbons, remember. So this has to have one more. And of course, actually, this has 1, 5, 6, 7. That's too many. There's nylon 6. Corrected. So we've got to add 1 carbon here, take 1 carbon away from there. When you go to this, so you switch the N, add 1 carbon to this chain, take 1 away from nylon 6,6, you've made nylon 6, which just has repeating identical units. So there's an example of two synthetic polymers that are very important industrially. But of course, polyamides are crucial to biochemistry. We've established this somewhat. Enzymes are polyamides, and they're sometimes referred to as proteins. They catalyze reactions in cells and may consist of hundreds of thousands of monomeric units, which are amino acids linked together through amide bonds. In spite of their large size, the reactivity of enzymes is often driven by a very small region of the polyamide referred to as the active site. The molecule that reacts with the enzyme is referred to as the substrate. What is the active site of an enzyme? Well, let's take a look at a typical example. Firstly, note that the active site of an enzyme is the region that the molecule the enzyme acts on, which is referred to as substrate, the region that binds the substrate. So whatever type of molecule the enzyme acts on, substrate, the region of the enzyme that actually binds the substrate, grabs hold of it, reacts with it, is referred to as the active site. It usually is only a small part of the enzyme's total structure. Okay. Point 3. The active site is a 3-dimensional region, and as such has chiral properties. It's chiral. The active site is often three-dimensional, and it's not surprising to find enzymes behave as chiral reagents and often produce specific enantiomers as products. When the enzyme and substrate combine, the two form a complex structure which interacts through ionic bonds, hydrogen bonds, or van der Waals forces. Now, one of the most studied enzymes is chymotrypsin. We looked at chymotrypsin in amino acids. It cleaves to the right of aromatic rings found in certain amino acids, such as tyrosine, tryptophan, and phenylalanine. It has over 200 amino acid residues. That's over 200 amino acid residues. But the active site, quite surprisingly, involves only 3 residues. Only 3 of the 200 residues. What's the rest of the enzyme for? It allows the molecule to adopt shapes necessary to bring these 3 residues in the proper 3-dimensional orientation to facilitate the reaction. Now, when we looked at amino acid chemistry and studied peptides, we did not look at any of the mechanisms of these cleavages. We talked about them. We used them to determine peptide structure. But what we want to do now, chymotrypsin, what is the trypsion? Chymotrypsin. What we want to do now is probably look at one of the most accepted mechanistic pathways for the functionality of chymotrypsin and the cleavage of the substrates upon which it reacts. Now, remember, chymotrypsin is one of the most studied of enzymes, and so we're going to draw, if you like, a reaction path which explains how chymotrypsin works. One of the things you need to note is that we're not going to draw all 200 amino acid residues. We're going to focus on only the 3 that are active. So what we're going to do is we're going to draw a squiggle and a big circle. Maybe I got to make it a bit bigger. And in this circle, we're going to call it aspartic acid. And we're going to place that aspartic acid at residue number 102 in the chain. And aspartic acid, remember, has a CH2CO2H. And we're going to start out with that CO2H deprotonated. Okay. Next, we have a large circle representing histidine. Histidine is found at residue 57. Oh, so we're going backwards. Well, not really, and you'll see in a moment. Histidine can tautomerize, so it has various structures. 2 tautomers of histidine. We're going to draw one of them. And our next residue is serine 195. 195? How can you go from residue 102 to residue 57 to residue 195? Don't think of this as a linear ordering. Think of it as the molecule folding. Because of its large chain, it can fold different sections so that residue 57 occupies space in between residues 102 and 195. Serine, of course, has a CH2, which has an OH. And there's obviously more to the amino acid residue. And what this is a hydrophobic pocket. And our reagent, or the species we react on, if you like, is a peptide bond where we get some C double bond O. And then we have a CH2 with an aromatic ring. We'll just write AR for aromatic ring. The aromatic ring fits well into this hydrophobic pocket. It's a nonpolar pocket that dissolves nonpolar ends. And hence peptides that have these nonpolar aromatic rings off them, right? Okay. Such as tyrosine, tryptophan, phenylalanine. They can dissolve in that pocket, which brings the amide section into close proximity. An electron movement fires like a gun. 2 electrons grab this proton. In fact, let's change the colors because it'll be easier to track if I use black or something to show the electron movement. The 2 electrons grab the H. We get this forming a new pi bond. These pi electrons go for the H on the oxygen. In fact, I'm going to redraw this. Let's go back to blue. We've got an O, H, okay. So these pi electrons grab that H. And those electrons here, off the oxygen, they go on the oxygen and a lone pair attacks the carbonyl. And you know, you push the pi electrons out and then the pi electrons come and kick out the N. So effectively what happens is the N leaves. Now, during the enzymatic reaction, a proton is picked up. So step 1. Produces so here we go again. Aspartic acid, 102. And we now have a CH2, C double bond O, OH. Because he's grabbed the proton. And then we have a squiggle down to histidine, HIS, 57. We have our CH2. And now we have our ring. And this time the H is down here. So step 1, produces this change in structure. We'll make that a little bigger. Serine 195. And now the serine is no longer an OH. It now has a portion of the peptide attached to it because it attacked the C double bond O. And off of the C double bond O you have the CH2 with the aromatic ring off of it. And I may, excuse me, I may just drop the CH2 and just directly show an aromatic chain, but it doesn't mean an aromatic ring bound right to the carbonyl. It means a group of carbons. In fact, it's probably more like a CH with more peptides off of here. So, rest of the peptide. Okay, and what do you have off of this? You get plus RNH2, where R is the rest of the peptide. So you've cleaved to the right of this aromatic amino acid. Okay. What's next? Well, effectively, what you can think of the first step as is the firing of a gun. You pulled the trigger. And what we're going to do in the next step is, we have to pull back the lever to fire the gun again. Pull back on the hammer. We have to reload it, if you like. Get it ready to fire again. So, the next step basically involves the loss of a proton and tautomerization. So this proton is lost. So in the next step, we're going to just lose in step 2 we're going to lose this proton, retautomerize, grab the H, the 2 electrons from the oxygen H bond go on oxygen. So effectively it's getting ready to fire again. The enzymes are getting ready to transfer some electrons. And I'll call this step 2 minus H plus. Now, what does that form? Well, let's come over here and draw the result over here, if we can. We're going to get back, so once we go from step 2, from this guy, we're now going to alternate back. So this will be my step 2 now. I'll draw what you get from this, minus H plus. What this effectively does is reproduce this structure which fired the electrons. The only difference is okay. So you have this setup. Now what happens? So we basically get the histidine and the aspartic acid into an electronic configuration where it can do that electron transfer again. Well, in step 3, going this way, we add H plus, but not just H plus. This time, a water molecule gets involved in the attack. So, and actually, let's fix those in black. So, the electrons moved here. Grab the proton and the electrons from the proton right there. Okay, So what we're going to do now is fire this electron gun again. It grabs the proton. Electrons go here, so histidine tautomerizes. It grabs the proton off water. And these electrons go for the carbonyl. Hydroxide tucks the carbonyl. And these two electrons go back here. So that when you're done, at the end of step 3, you get the OH. You get this histidine again. You get this O minus, and you get the carboxylic acid. You get an R, or if you like, an AR, aromatic CO2H given off. And you've cleaved, effectively cleaved, the carboxylic acid, so that goes off. Now obviously, to go back to this, we've got to do the same thing again. Minus H plus, and reconfigure the histidine. So he grabs a proton, electrons move here, he grabs the proton. So we reconfigure this to go back to the structure we had in step 1. Now the first structure often use the symbol E plus S, representing enzyme plus substrate. E bonded to S usually means enzyme combined with substrate in some fashion. Overall, these 3 steps show the cleavage of a peptide to the right of tryptophan, tyrosine, or phenylalanine. This aromatic peptide that fits in this hydrophobic pocket. This shows the cleavage, pointing out that in this large enzyme structure of chymotrypsin of over 200 residues, only 3 residues are actually involved in the chemistry. That's quite amazing. The last thing we want to talk about with regards to amide chemistry is referred to as the competitive inhibition of an enzyme catalyzed reaction. Now, in order to understand this, we have to give you some background information. Folic acid is used as a vitamin. It's important for pregnant mothers involved in metabolism of all living things. And some bacteria require the molecule folic acid for reproduction. Folic acid looks like this. Okay, so here's a molecule referred to as folic acid. Folic acid contains the compound para-aminobenzoic acid, this molecule. That fragment is drawn in black in the folic acid molecule. Para-aminobenzoic benzoic acid. Now, para-aminobenzoic acid, PABA, is a UV-absorbing compound used as an ingredient in some sunscreens. PABA is incorporated into folic acid by an enzyme reaction. So if you like, this molecule is built enzymatically where PABA is inserted into the molecule via the enzyme. Many infectious bacteria require folic acid for reproduction, and they have been treated using sulfa drugs of this structure. Notice the similarity. A sulfanilamide. Okay. These contain the sulfanilamide unit in place of the carboxylic acid unit. The sulfanilamide unit can bind to the enzyme. See, the enzyme grabs onto carboxylic acid and incorporates it. The sulfanilamide unit can bind to the enzyme that would normally put folic acid in and block it. That means PABA is not inserted into the molecule to create folic acid. That means no folic acid is available to the bacteria. Bacteria can't reproduce, the bacteria die. The sulfanilamide competes for the active site of the enzyme. Because it competes for the active site of the enzyme, the sulfanilamide binds to the enzyme can't pick up the PABA, it can't make the folic acid, the bacteria die. The sulfanilamide is competing and inhibiting the reaction of the enzyme, just as in the title. Competitive inhibition. The effect is called competitive inhibition of an enzyme catalyzed reaction. Now, sulfur drugs are often referred to as narrow-spectrum antibiotics because they're only successful against bacteria that require folic acid for reproduction, and not all bacteria require folic acid. This limited effectiveness of sulfur drugs is caused by the fact that not all bacteria require folic acid for reproduction. Some bacteria can actually produce their own PABA, which will compete against the drug, requiring higher doses, which can be problematic. Okay, so this is a nice example of how understanding the active site of an enzyme, understanding the chemistry of the substrates and how they react, how they function in a cell, can be used to develop drug strategies for the treatment of disease. Okay. Well, that's it for amide chemistry. We have one more carboxylic acid derivative to look at. That's nitriles, and we'll take a look at that in the next Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast lecture. I thank you for listening.